Imagine a computer that thinks like you, not just a tool that follows instructions but a machine that can understand, learn, and adapt in real time. This isn't science fiction, it's the emerging field of neuromorphic computing, not just a faster calculator, but a machine that learns and adapts like a living brain. Traditional computers, while incredibly powerful, are limited by their architecture. They process information sequentially, which can be a bottleneck for complex tasks. This is the promise of neuromorphic computing. By mimicking the brain's structure and function, these systems can handle tasks that are currently challenging for conventional computers. Traditional computers are good at crunching numbers, but they struggle with tasks like pattern recognition and learning. They rely on predefined algorithms and lack the flexibility to adapt to new, unforeseen situations. Our brains, on the other hand, excel at these things. We can recognize faces, understand languages, and learn new skills with ease. This is because our brains are highly parallel and adaptive systems. Neuromorphic computing aims to bridge this gap. By creating chips that function more like our brains, we can develop machines that are not only faster, but also more intelligent and capable of learning from their experiences. Instead of relying on separate processing and memory units, neuromorphic chips are built like networks of neurons and synapses. This allows them to process information in a more integrated and efficient manner. They mimic the structure of the human brain. This means they can perform complex tasks such as pattern recognition, decision-making, and learning with greater efficiency and speed. These neurons communicate with each other using spikes of electrical activity, just like their biological counterparts. This method of communication is not only fast but also highly efficient, allowing for real-time processing and adaptation. This allows neuromorphic systems to process information in parallel and learn from their experiences. As a result, they can adapt to new information and environments much like a human brain, opening up new possibilities for artificial intelligence and machine learning. Think of a traditional computer like a library. Imagine walking into a grand old library where information is stored in a very organized manner. Each book has its place on a specific shelf, and everything is cataloged meticulously. Information is stored neatly on shelves, much like data is stored in a computer's memory. Each piece of information has a specific location, making it easy to find when you know exactly what you're looking for. And accessed by a librarian who acts like the computer's processor, retrieving the information when needed. The librarian knows exactly where to go and what to look for, making the process efficient for straightforward tasks. This system works well for structured tasks, such as finding a specific book or piece of data. However, it's inefficient for more complex tasks, like image recognition or pattern detection, where the information isn't as neatly organized. Now imagine trying to find a specific face in a crowd using the library analogy. It would be like asking the librarian to find a book without knowing its exact location or even its title. The librarian would have to check each book individually, a time-consuming and labor-intensive process. This is similar to how traditional computers struggle with tasks that require recognizing patterns or making sense of unstructured data. A neuromorphic chip, on the other hand, is like a vast network of interconnected neurons. Instead of relying on a single librarian, it uses many small processors working in parallel, much like the neurons in our brain. Each neuron can recognize a simple pattern, like an edge or a corner. These simple patterns are the building blocks for more complex images and concepts. When these neurons work together, they can quickly identify complex objects and patterns, much like our brains do. This allows neuromorphic chips to excel at tasks that are challenging for traditional computers, such as real-time image recognition and decision-making. Neuromorphic computing has the potential to revolutionize artificial intelligence. Imagine robots that can learn and adapt to new situations just like humans. This technology could also lead to breakthroughs in fields like medicine, finance, and cybersecurity. Imagine medical devices that can diagnose diseases with unprecedented accuracy or financial algorithms that can predict market trends with greater precision. But perhaps the most significant advantage of neuromorphic computing is its energy efficiency. Our brains use remarkably little power to perform complex tasks. Neuromorphic systems aim to achieve similar levels of efficiency. Researchers around the world are working to develop neuromorphic chips. Two prominent examples are Intel's Loihi and IBM's TrueNorth. Loihi is a self-learning chip designed for tasks like object recognition and decision-making. It has been used to control a robotic arm, navigate a maze, and even smell different odors. TrueNorth, on the other hand, is a low-power chip that excels at pattern recognition. It has been used for tasks like image classification, speech recognition, and even detecting anomalies in financial transactions. Section 5. Neuromorphic computing in action. The potential applications of neuromorphic computing are vast and varied. This revolutionary technology mimics the human brain's architecture and processes, enabling machines to perform tasks with unprecedented efficiency and adaptability. Let's explore a few examples to understand its transformative potential. Self-driving cars. Neuromorphic systems could enable autonomous vehicles to make faster and more reliable decisions in complex environments. These systems can process vast amounts of sensor data in real time, allowing the vehicle to anticipate potential hazards and navigate safely through busy streets. Imagine a car that not only reacts to immediate obstacles but also learns from past experiences to improve its driving over time. This could significantly reduce accidents and enhance the overall safety of our roads. Medical technology. Imagine prosthetic limbs that can learn and adapt to the user's movements. These advanced prosthetics could provide a more natural and intuitive experience for the user, improving their quality of life. Or brain-computer interfaces that can restore lost senses. For instance, a person who has lost their sight could potentially regain some visual capabilities through a neuromorphic interface that translates visual information directly to the brain. Neuromorphic computing could make these science fiction concepts a reality, bringing about a new era in medical technology where the boundaries between human and machine are increasingly blurred. Robotics. Robots equipped with neuromorphic chips could work alongside humans in factories, hospitals, and other settings. These robots would not just follow pre-programmed instructions but could learn from their experiences and adapt to new tasks. They could collaborate with each other and with human workers, creating more efficient and flexible work environments. This could revolutionize industries by enhancing productivity and reducing the need for human intervention in repetitive or dangerous tasks. Section 6. The road ahead for thinking machines. While neuromorphic computing holds immense promise, there are still significant challenges to overcome. One major hurdle is scalability. Building large-scale neuromorphic systems with billions or even trillions of artificial neurons is a daunting task. Another challenge is developing effective algorithms and programming paradigms for these new types of computers. Traditional software development methods may not be suitable for neuromorphic architectures. Section 7. Challenges in the quantum realm. As we delve deeper into the world of neuromorphic computing, we encounter challenges that border on the philosophical. How do we ensure that these intelligent machines remain under our control? What are the ethical implications of creating artificial systems that can think and learn like humans? These are questions that we must grapple with as we continue to develop this transformative technology. The future of intelligence may depend on our ability to navigate these complex issues. Section 8. The future of intelligence. Neuromorphic computing has the potential to reshape our world in profound ways. It could lead to a new era of artificial intelligence, one where machines can learn, adapt, and solve problems in ways that were once thought impossible. Imagine a world where robots work alongside humans, augmenting our abilities and helping us to solve some of the world's most pressing challenges. Imagine a future where intelligent machines help us to understand the universe and our place within it. This is the promise of neuromorphic computing, a future where the line between human and machine intelligence becomes increasingly blurred.